This video looks at the last of our three forms of heat transfer. We've done conduction, we've done convection, and now we're going to talk about radiation. And radiation is quite special because it's the only one that can happen in a vacuum. So we need to know how heat radiation reaches the Earth from the sun, describe heat radiation as a wave and maybe compare it to light. And then we've got to talk about colour and know that dark objects are better emitters and absorbers of heat radiation than light coloured objects. So I like this picture. This is a hairdryer. You would never turn your hairdryer on and see this, but this is what's known as a thermal image. So instead of looking at the light from your hairdryer being reflected off your hairdryer, we are looking at the heat, or we're looking at the temperature of the hairdryer itself and the air particles around. So this is a camera that is sensitive to light, to heat rather than light. What is this radiation? The first question to ask is, if the sun is warming the Earth, and if you've ever been on holiday and sunbathed, then you'll know that the sun heats up the Earth. That's quite obvious. There's no particles in space. It is a vacuum. We talked about that right from year 7. So how on earth does the heat energy get from the sun to the Earth? It can't be conduction and convection because there are no particles, so it's got to be by another method, and that method is called radiation. Heat radiation or infrared radiation. It's something called an electromagnetic wave, which we will come to in the next unit. It's very similar to light. It's in the same sort of family as light, if you like, and they can travel through empty space just like light can. So too can heat, and heat does this form of heat transfer does not need any particles, but conduction and convection do need particles. Okay, a couple of key words. If you heat an object up, then that object will emit heat. If an object is cool, it might absorb heat. So the idea of giving heat out or transferring heat from you is called emitting, and the idea of transferring heat into you or into a body is called absorbing. If you are warmer than your surroundings, so if you find yourself stuck in a fridge, then you would be warmer than the fridge, so your body will emit more heat than it absorbs because you are hotter than the fridge. So this will mean that you cool down because you are emitting more heat. If you then find yourself in the desert, now some deserts might be hotter than your body, more than 37 degrees, so if you are cooler than the surroundings, so if your body is cooler than the desert, then your body might absorb some heat, and this is where you could end up heating up quite dangerously. So if you are cooler than your surroundings, then you will absorb more heat. The heat will be transferred into the body or your body, and this will happen more than emitting. So if you put any object in a fridge, it cools down, and if you place any object in a desert, it will warm up, and this is to do with how much it's emitting and absorbing. So I wanted to remind you of the two practicals you did in lesson. The first practical was filling a silver and a black can with boiling water, and you measure the temperature, start your stopwatch, and then you record the temperature for every 15 minutes to see how much the silver can and the black can cools down. This was to do with emitting heat, because you were seeing how good or bad the black and silver were at emitting heat. And then we looked at absorbing heat, and to do this we had a metal and a metal sheet, a silver metal sheet and a black metal sheet, and we placed them on the desk, and when we placed them on the desk we put a strong light in front of them, and this light was giving off heat, so it was a source of heat radiation, and we compared how well the silver and black absorbed the heat radiation by looking at the temperature increase over time. Now what you should have found is that the black can cooled down the most, or the black can emitted the most heat, and the black plate heated up the most, or the black heat absorbed the most heat. Based on our two practicals, we said that hot black objects cool down faster because they are better emitters of heat radiation, and cold black objects heat up faster because they are better absorbers of heat radiation. So black is the best emitter and black is the best absorber as well. Be careful, other colours do emit and absorb, but black just happens to be the best. And also anything that's shiny shiny things don't absorb or emit very well, whereas dark matte objects, and what we mean by matte is something that's not shiny, they emit and absorb very, very well. So I'll just do a quick true and false. Infrared radiation travels in straight lines. Well, you remember from your studies in year 8 that light travels in straight lines. So that's definitely true because it's from the same family as light is. Infrared radiation can travel through a vacuum. Well, that's what this whole session's been about. Definitely true. Infrared radiation requires particles to travel. No, it doesn't, because conduction and convection need particles, but radiation doesn't. Infrared radiation can travel through thick walls. It can't really, because if you imagine if you shade yourself from the sun, you could do that by going inside and the sun won't get through the light or the heat. Matte surfaces are best at emitting infraradiation. So matte means not shiny, and we said that's definitely true. Infrared radiation travels at the speed of light. Well, it does because it's part of the same family, electromagnetic radiation, as light. That's definitely true. And finally, shiny surfaces are best at emitting infrared radiation. Well, that's false because we said matte colours, matte surfaces are the best at emitting radiation.